is a 30-minute presentation for almost like 30 minutes, and then we allow the audience to ask their questions. After that, we'll ask you to leave us to ask further questions. Thank you.
Assalamu alaikum everyone. I'm Hafizur Rahman. Today I'm going to present my thesis titled as Whole Body Loco-Manipulation in Quadruped Robots for Human Robot Object Handover. So my advisor is Dr. Mohammad Faiz Al-Masrullah. My committee members are Dr. Sami Al-Farid and Dr. Rahman. So quadruped handover is not as like a simple locomotion or manipulation task. It's a complete whole body control that includes the perception, the planning, the control, and then the compliance interaction with the receiver for the handover task. So, like this, we'll present our, we'll continue our presentation in these roadmaps. We'll try to follow this roadmaps here. So we'll start with the introduction and describing the challenges and the problem statements. Then we'll go into the literature review. We'll discuss about the research gap that we found from the literature. Then we'll go for the methodology where we'll discuss about the model of these robots and also the control system that we used. Then we'll start, and then we'll go to the simulation and the radars, and then closing by discussing the limitations and the feature works. So handover is simply a pick and place type of task. In pick and place task is grab from one place and keep it in another place. But in handover, it need to be synchronized, the pose, the timing. Also, it need to detect the transfer so that it can grab the bottle and it can the robot can understand that the transfer is completed. So while we are using quadruped with manipulator, quadruped and manipulator has a wide range of workspace. It can move from one place to another place. Human don't need to go to the robots to pick the to do the handover task. Though it comes with some hardness, there are some issues with while it's manipulating. Because of the motion of the base, it might blur the perception, and it also can create the occlusion while moving the arm. It might come in front of the camera. So we'll more discuss about the challenges here. The first challenge that we mentioned is the perception robustness of this work. It might degrade the occlusion, it might degrade the detection of that camera because of the locomotions of that quadruped. And we also have the base arm coupling issues. While the arm is moving, it changes the center of mass of the base. So that's why it needs to be stable while the arm is moving in that workspace. And we also have the contact safe transfer. So in handover, the major issue is contacting with the external environments, which basically gives the return, which makes the robot more unstable because of the interaction. So we have to consider this one as well, and also mostly the real-time feasibility issue. The feasibility issue is showing that how stable the robot can be within certain pose, and also the limits, torque limits, the acceleration limits should be bounded. So as the work treats handover as a complete closed loop system integration problem. It's not just an independently tuned model separately. Then we find some research here from the literature that we consider three gaps here. So first, the dynamic locomotion, then the perception handover, and the compliance control. We discuss in next slides about the literature review. So we complete this problem statement like this. So we develop a quadruped manipulator handover framework that remains safe and stable and reactive while coupling between the locomotion and manipulation and in uncertain perceptions model, and also it considered the contact error during the object transfer. So these are the contributions of this work So the first contribution was that unified model of quadruped robot for the robot to human handover pipeline. So we also, as we mentioned, it's an interaction-centric work. It considered from perception. It developed from perception to planning to control framework for this handover task. And we also consider the compliance grasp and transfer detection, which makes the handover more reliable in terms of the force changes and the factor. Then we also tried some multi-payload benchmark. We tried different payloads to benchmark the stability of this controller. And the scope of this work is we studied this in simulation in gazebo. We use an unitary quadruped with an Innova arm, and we have the 3 fingers gripper. So from the literature, we found several literature related to the whole body control, like with MPC, like predictive control, and the perception and the compliance related. This does not mean that those papers are lacks of these things. They are basically considered in that dimension. The first 3 papers, they are basically they mostly focus on the quadruped robot for quadruped robot in predictive control to make it more stable and to make the locomotion more robust, so that it don't fall, or so that it don't destabilize because of the arm movements. And the 5th paper, they also consider the human robot handover task. In their case, they try to do the task from human to the robots, but they didn't consider the compliance control. So in our work, we try to combine all these 3: the predictive maintenance, the MPC, the perception, the compliance, all together. So from this literature, we can position the thesis like this. We integrate the complete system. Then we use the interaction-based safety features, and we also try some safety distance and main trajectory behaviors, and also run some benchmark to justify to check our controller in terms of different payloads. Okay. So this is the complete perception to control framework. We have 5 layers of control framework. Initially, first we have the perception, then the task sequencing, then we have the MPC planning. Then from the MPC planning, we go to the whole body control execution to the interaction stack. So perception gives us perception mainly gives us the main position of the objects in that environment, and task sequencing giving us in which in the complete FSM in which state is on, and MPC based on the perception model, based on the perception detection, MPC creates the trajectory, and whole body control try to follow that exact trajectory. And interaction stacks helps us to make the interaction more safe in with the receiver end. So from here we start this is the perception pipeline we use. So initially we use the segmentation model, color segmentation model for detection of the object, and also the gripper in simulation. We also use the depth sensor to measure the distance from the base, and then we transform them from the camera, from the object to the camera, from the camera to the base, and base to the world frame. And now we have this the second layer, full dynamics model of these robots. In this dynamics model, on the left side, we have the robot inertia pole, inertia response, which is combined with the generalized inertia with the nonlinear dynamics. Then on the right side is divided into sections. It's on the leg actuators and the contact interaction phases. So for the leg actuations, we use the joint torques from the legs and from the arm. And the contact interaction type, we have total 5 contact points, 4 in the legs and 1 in the end effector. And we also consider these base disturbances in these complete full body dynamics. So from the complete full body dynamics, then we transform that into a handover task, handover task frame, so that for the end effector task frame, so that the end effector can make the can make that complete task in that real space. And this and also this workspace, they tries to split the locomotion and manipulation part, which helps the locomotion and manipulation. While it manipulating the arm, it try to stable the base so that it don't make an abrupt motions. Then we have this centroidal MPC formulation. This centroidal MPC is try to reduce the full body dynamic dimensions, so that it makes easier for the controller to compute the complete dynamics of this robot. So the MPC dynamics is divided into the centroidal momentum is divided in 2 sections. First one was the linear, and then we have the rotational dynamics. So MPC also considered some constraints, like this. It should be the MPC helps to make the robot consider some constraint, so that it makes the robot, while it's moving, while it's manipulating its arm, more stable. Those constraints are the joint limits, the actuator limits, and also the main friction points of the robot base legs. So from the MPC we got the outputs, some output. Those are the main desired trajectory and also the base posture. From these outputs from the MPC is fed into the whole body control. Then this whole body control is try to execute that exact trajectory that we got that generated from the MPC. And this hierarchical whole body control divided in 3 priority tasks. As we said earlier, that MPC has to maintain some constraints. That's why whole body control has these 3 priority tasks. So first task is basically try to maintain that complete constraints. And we also have the motion tracking as a priority 1, and we also have the priority 2 as the interaction phase. And from here we got the outputs of desired torques and desired position of that joints, and that we are going to deploy on real robots. Okay, now we have the interaction part. So in that interaction part, we have the Cartesian impedance control and also the rotational impedance, which helps the arm to make it more compliance with the interaction while it's interact with the objects or interact with the receiver hand. Okay, now we have this force-based release gripper. So while we try to hand over the object to the receiver hand, we compute the force changes in the gripper, so in the robot gripper, so that it can understand that when the handover is completed. It's based on the sequence and the load transfer releases. So the load transfer the threshold was we put it as a 15 Newton meter. So based on the handover task, if the threshold is more than the 15 newtons, it try to it goes to the initial it goes to that release state to release the objects for the receiver hand. Okay, so this is the complete setup. Okay, so this is the complete experimental setup in Gazebo. We use this table as a human proxy, and we use a simulated human hand as a object receiver, and we also have the object as a we consider it as a cylindrical object, as a bottle, and we use the four-stroke sensor at the wrist to detect that load transfer, and we also use two cameras, one at the wrist camera and one at the base camera. We'll explain why we use these two cameras. Okay, these are some runtime parameters while we're completing our control, while we're doing the controller task. So for the MPCs, for the MPC layer we have the horizon of 1 second, and the WPC which calculates in 500 hertz per 500 cycles per second, and for the contacts we use the friction coefficient for 0.7, and impedance, these are the gains, and for the admittance we use these parameters, and we also use for the gripper we use the hybrid control for the gripper as well. And these are some hypotheses we're going to show in the result section. We'll try to show the whole body stability, the compliance effectiveness, then the safety wire approach, the pipeline coherence, like how the complete state machine is working, and also the payload scalability, like how the payload benchmark, how the controller works in different payloads. So we start with this peak-up phase. So in peak-up phase has these 9 states that we discussed earlier. So initially it's wait for the MPC to initialize, then it's stand and detect the bottle, and then try to reach the bottle and grab it. After the grabbing it, it try to lift the bottle. Then it's transient to the handover states. Here the main thing is it's not it's not like that. It's the robot just going to the fixed position. Here perception model is helping to detect the bottle and calculating the exact frame pose and position of in that environment to grab the bottle or grab that object robustly. So for the perception, we can see that for perception results, throughout the time the perception was always more than the 70%, and it's try to keep it as a more than 90%. And there is, from these figures we can see the first figure is while it's so for the blue line we can see that it's a leg RMS. So the leg RMS throughout the time is try to maintain within the limits, and the arm RMS, you can see when it's try to lift the object, we have some oscillation due to the peak phase of the due to the peak up and lift the objects. Then we can see the finger RMS. So initially the finger was try to grab that bottle, and then while it's lifting, we also have the ingredient in that finger. Then we have this gripper compliances. So based on from 0 to 1, it's for 0 it's the gripper is open, and for 1 it's closed. So when the gripper is initialized to grab the bottle, it starts. It just don't start abruptly to grab that bottle. It's try to adapt with the bottle position and in the gripper, and based on that, it try whenever it needs to increase the gripper position, it's try to adapt. So we can see that when it try to lift from here. In that period of time, it's the gripper commands was bit more. Okay. This is the handover, the main handover task here. So from as we said, from the pickup we start the handover phase. So for handover phase, it detects the bottle, and also it's detect the gripper, the external receiver hand. Then it's try to reach to that position, and then it's wait for. Then it compliantly goes that place. Then wait for the receiver to grab it, and after grabbing it, then it releases the objects. So the release is based on the force changes due to the handover between the robot arm and the receiver arm. So this is the MPC layer for this works for the handover phase. So we can see from for the handover phase, for the MPCs are trying to these dotted line are the desired position, and the dotted line is the desired position, and each x, y, z in every direction is trying to reduce that distances. But we can see we have this error the error is very high. The reason is that in that position it try to goes from the lift position to in front of the receiver hand, but it don't abruptly go to that receiver hand. It try to compliantly go slowly go to that receiver hand, so that it makes the robot more compliant in that phase. These are the error it shows. So as I discussed, the same error we found in that period of time for the compliant place from the pickup to the receiver hand. So that's why we found this error, and throughout the time it's tried to reduce that error as well. Okay, and this is the graph. These are the graph for the base stability and COM dynamics. On the first one, you can see the in this period it's when it was walking and tried to align with the receiver hand, we saw some oscillation, and throughout the time it tried to reduce the COM velocity. This center of mass velocity represent that throughout the time the robot was stable while doing the handover task. And we have seen that the base height, it try to maintain the base height of 0.33 meter throughout the handover tasks. Okay, so these are the graphs to show the force stability on the ground on the ground legs. So as you can see from when this manipulation task starts, the ground legs has not much change in the ground reaction forces, because while it's trying to manipulate the arm, it's trying to keep the base posture as constant as possible. But we can see there's some oscillation here. These are basically when it's trying to walk a bit and align with the handover, align with the receiver hand. Then this. Then this figure shows the support polygon. The middle is considered as the base, the black square, and we can see the COM in the middle of this base, and these four are the foot position. We can see that throughout the time it's trying to maintain the COM in the central position, and the lowest position was the lowest. When the distance from the COM to nearest legs was in this period of time while it was trying to walk. Okay, so this figure also shows how the legs, the arm, and the fingers is working. We can still again see that throughout the time the legs try to stabilize the system, except the walking and walk aligned part. And for the arm, we can see as it's for the complete handover task, throughout the time it try to grab the bottle. So the hand RMS is quite high in every time. And also in this period, from this period of time, we can see these are the clearance and compliant place time. So in that period of time, we also see higher RMS values in the arm. And Okay, and also we can see in the finger throughout the time while it's holding the bottle, and then while it's release the bottle to the receiver, we can see the RMS changes after handover. Okay. So this is the force-based load transfer detection. As you can see, it's when it's grabbed the bottle, we have the changes in the force. The delta force is changing. Because of that force changes, it's understand that the receiver hand is grab the bottle, and then based on that, it's release the bottle to the receiver hand. You can see from while it's starting to differentiate the delta F, it start the command for the release, and then it's executed in this period of time. And throughout the time, how the gripper controller, the grippers are working, showing in this graph. So as you can see, the when it's trying to do the handover task here in this period of time, it's released the gripper. It released the robot gripper for the receiver hand. In this time, it's not just abruptly release it. It's try to understand that its grab is successful, then it release the gripper. And we also show that the distance safety throughout the time. This distance is from the end effector to the end effector to the receiver hand. It's try to maintain a distance from the receiver hand so that it don't collide with the receiver hand during the handover task. And we also have the perception detection model. So the perception throughout the time try to maintain more than 90%, but there was oscillation because of the compliance place during the compliance place states. That's why we saw some perception drops here. Okay, now we start the multi-payload benchmark. So for the multi-payload benchmark, we use 4 loads. For the first dose is for the complete handover. Firstly, we use the 500 gram objects, then 1 kilo, then 1.5 kilo, then 2 kilos. So we can see that for the total trial duration for the handover, if we increase the payload, it increase the total time duration. It's mainly because of that compliance place state. So in that compliance place state, if we increase the payloads, it takes more time to reach to the receiver hand for the handover task. And here with this, and also we can see for if we increase the payloads, the effort RMS for the arm is increased because of the payloads in this handover task. And also one thing to notice that if we increase the payloads for if we increase the payloads throughout the handover task, the leg RMS try to maintain the leg RMS effort. It try to maintain the same values for each of the payloads, which means for the payload differences, the leg RMS it didn't change. The stability of the posture was very robust in different payloads. Now here we can see for the compliance for the handover task for different payloads, how the posture was for these quadrupeds, and this graph shows the CUM projection. Here we can see for the 2 kilo or 2 kilograms of payload, for the 2 kilogram payload, which we can see an more cluster area for the CUM projection, because in that period of time it try to maintain more stability during movement of the arm. Okay, so these are 4 videos for the handover task for 4 different payloads. The main thing we can show that for the 2 kilogram of we can see a very abrupt motion in the robot, and also it try to push and it can't it can't accurately lift the bottle because of the higher arm utilization, arm torque utilization needed for this one. But you can see the handover task is not completed in that part, but all three of these three payloads, it was successfully completed the handover task. But for 2 kilo weight, it couldn't complete the handover task yet. Okay. So this is the graph. It shows the arm torque utilization throughout the 4 different payloads. We can see while it's increasing in the payloads, we can see the arm utilization of arm torque utilization is increasing because of that payload weights. The payload increases. Okay. Now we also tried to show the ablation test based on with the compliance control and without the compliance control. If we can see these rates are without the red arrow shows without the compliance control, and the blue one is our our model with the compliance control. So in the video we can see that without the compliance control, whenever it touches the bottle, it shows a very abrupt. Shows very abrupt motion in the arm. That's why it just killed the complete controller. And we can see the constraint violation here was too high, while the controller was stopped. And also we saw the dynamic violation also way too high compared to our with the compliance controls. Okay, so the main findings and the hypothesis of this work is we try to show the payload benchmark, which helps us to understand at which point this handover task may fail, and we also shows the force-based load transfer detection for all loaded trials, and we also shows that the hand effector always try to keep distance from the receiver hands, and we also say that the 9th state and 11 handovers executes the throughout the handover and peak states. And for the fifth hypothesis, we show that for the 4 different payloads, for the last one was has the issue while doing the handover tasks. Okay, so we have some limitations of this work. The current limitations are these. We conducted this on simulation, and so we only try on one object geometry, only the cylindrical based bottle, and also we tried for the receiver we tried an stationary hand. We didn't consider as a human moving hand, because of the limitation in the simulation, and we also tried this statistical analysis for one single trial based on for the multi-payloads. And for the future research direction, we will try to validate this complete controller for the real robot implementation, and make also try to make the gripper and control more payload aware, so that if the payload increases, based on that it's adapt the gripper and also the arm for the complete handover task. And we also for the future direction, the human aware adoption should be more should be more it should be included more to understand the human intent, and also how human pose is, how human or receiver hand is moving. These are some resources related to handover, manipulation, locomotion, and whole body controller, and the perception models we used from these sources. And these are some research outcomes that we get from these thesis. first of all, we trying to publish this complete work in a journal, and then we also submitted one paper in a conference, SSG conference in this year, and it's accepted. And we also published one literature review in IEEE Access, and it's already in online. And I want to acknowledge, I want to thank Allah for the guidance and blessings throughout the time of my thesis. I want to thank my families and friends, and I want to also thank the advisor, the co-advisor, the department faculty for their guidance and encouragement. And a special thanks to IRCSML and KFUPM for the research support, for the facility and the collaborative research environment. And finally, I want to thank all the colleagues and friends and the KFUPM Bangladeshi community and the KFUPM for the complete support throughout my master's journey. Thank you everyone. And this was if you have any questions, you can. Thank you.
So because of